Okay, first of all, I have not gotten the exams graded. I didn't get them until yesterday. So I have not had a chance to grade exams. Second of all, as mentioned prior to the break, there is nothing that will be due this week. So you don't have any homework, so you don't have any quizzes this week. However, if you look at Blackboard, you would know that there is a bonus opportunity Thursday night if you, it's called Conversations with Chemists. It's held by the local American Chemical Society section. If you want to attend, and if you want to take notes, that could be a 10-point bonus towards the end of the semester. To be able to do so, you're going to have to send me an email so that I can send you a copy of the flyer. And that is Thursday night at 7 p.m. and it's on Zoom. So it's not in person. Let's see. I will say one other thing. If you are on the, I believe the W deadline is next Monday. If you are wondering whether or not to withdraw from this course, or you can always let me know and I'll get your test graded. I'll make sure your test is graded so that you know where you stand. I mean, I plan to get them graded anyhow. It's just this week is particularly busy week. So again, if you are going to be, if you are on that cusp of wondering, you can come see me and I'll grade your exam individually. And figure out where you stand. Let's see. I think that's all the announcements. So what we'll be doing today is we're going to be picking up where I left off on Tuesday prior to spring break with a conversation that is the introduction to dimensional analysis. And if you were not here on that Tuesday, or I may have talked about before then, I know I'll print them for this. I do have a handout that is a flow chart that can help you figure out what conversion to perform at what time. And so you can come grab one. Yes.
You know when the referee draw from
I believe it's Monday next week. That's what I have on the syllabus is the 7th. Okay, so we're going to pick up where we left off on the Tuesday prior to spring break with the introduction of dimensional analysis. Dimensional analysis is something you've done all of your life, whether you realize it or not. How many inches are in 3 feet? Well, you multiply that by 12 and get 36 inches. How many eggs are in 2 dozen? Well, there's 12 eggs in a dozen, so you would tell me there's 24 in 2 dozen. So it's something you've done all of your life, but when we get into dimensional analysis, we start getting into specific conversion factors. And this dimensional analysis is also known as stoichiometry. So it's just a fancy name for chemical dimensional analysis. Prior to the break, I introduced 3 conversion factors that we will be using out of 4 for dimensional analysis. The first is Avogadro's number. I introduced this when I introduced the concept of a molar mass. And essentially with Avogadro's number, it is always 1 mole is equal to 6.022 times 10 to the 23rd. And you know to use Avogadro's number anytime you see the term atoms, ions, or molecules. That's going to be your indication that you're going to need to use Avogadro's number as one of your conversion factors. The second conversion factor we talked about is the molar mass. And the molar mass is however many grams is equal to 1 mole of that substance. You will use the molar mass as conversion factor anytime you are working with grams. And then the last one, there's actually 2 variations to the mole to mole ratio, but we only talked about one per spring break, and I'll introduce the second one on Thursday of this upcoming week. But the mole to mole ratio allows you to convert between 2 unique chemical formulas. That can be an element symbol and a compound containing that element. So basically, as long as the formula is different, then you use the mole to mole ratio. And this is where we're going to pick up today, is we're going to work multiple examples using these 3 conversion factors. I'm letting folks catch up to what's on the screen. Okay. Oops. So let's just look at some examples. Let's go with how many moles of sodium oxide contain 1.5 moles of sodium. With all dimensional analysis, the first thing you're going to do is identify what you were given. You were given 1.5 moles of sodium. The second thing you do is identify what you want to solve for. We want moles of sodium oxide. Now, we're going to start picking this thing apart. When I pick these things apart, the first thing I do is I pick apart the formulas of the substances.
And what I see is I see two substances. Because I have two different formulas. That means I'm going to need the mole to mole ratio. So I look at the chemical formula of sodium oxide, and what I see is there's 2 moles of sodium in 1 mole of sodium oxide. The next thing I'm going to do is I'm going to look at what I was given. I was given moles of sodium. Okay, well, I have moles of sodium already, so that's okay. And the next thing I do is I look at what I wanted to solve for. I wanted to solve for moles of sodium oxide. Well, I have moles of sodium oxide. So I already have the units that it talked about. So this is the only conversion factor I'm going to need. So we set up the problem with the piece of information we were given. So we'll put the 1.5 moles of sodium in the numerator. Now we'll use our conversion factor. When we put in this conversion factor, the moles of sodium must go in the denominator so that they can cancel out, leaving moles of sodium oxide in the numerator. The moles of sodium had to go in the denominator so that the unit and the substance cancels. When we're dealing with stoichiometry, it's not sufficient for the unit to cancel. The unit and the substance must cancel. When you perform this calculation, you get 0.75 moles of Na2O as the answer. Questions? Let's look at another example. How many moles of sodium chloride contain 26.15 grams of chlorine? We identify what we are starting with according to the beginning of the problem, which is the 26.15 grams of chlorine. We identify what we want to solve for, which is moles of sodium chloride. Now we pick it apart. The first thing I'm going to pick apart is I'm going to look at the substance. And I see 2 different formulas here. So 2 substances means I'm going to need the mole to mole ratio. In this case, there is 1 mole of chlorine in 1 mole of sodium chloride according to the formula of sodium chloride. The next thing I'm going to do is I'm going to pick apart what I've been given. I have been given grams of chlorine. Anytime I see grams, that means that I'm going to need the molar mass. So I looked to the periodic table, and according to the periodic table, 35.45 grams of chlorine is equal to 1 mole of chlorine. The next thing I do is I look at the other unit. In this case, I want moles of sodium chloride, which I already have. So I'm going to need 2 conversion factors in this particular problem. I start with the 26.15 grams of chlorine. My first conversion factor has to have grams of chlorine in it. So I'm going to use that 35.45 grams of chlorine is 1 mole of chlorine. Of that conversion factor, the grams had to go in the denominator so that the unit and the substance canceled, leaving moles of chlorine. Now I have moles of chlorine. But that is not what I was asked to solve for. I was asked to solve for moles of sodium chloride. Therefore, I'm going to use the mole to mole ratio. According to the mole to mole ratio for 1 mole of chlorine, I have one mole of sodium chloride. The mole of chlorine went into the denominator so that the unit and the substance canceled out, leaving moles of sodium chloride. Now I key it into the calculator. 26.15 divided by 35.45 means that it's 0.74 or 7, let's see, I need to do that. 73766 moles of sodium chloride. Now I need to check for significant digits. In my starting quantity, there were 4 significant figures. In the molar mass, the mass portion had 4 significant figures. The mole is infinite, and mole to mole ratios have infinite numbers of significant digits. So since the measurement with the fewest had 4 significant digits, my value must have 4 significant digits. And I should have changed this. Let me change this number. I rounded too early. Anyhow, when I do this, when I round it, it's 0.7377 moles of sodium chloride. Questions? You're going to have to jump in if you have any questions. Let's look at another example. How many moles of oxygen are in 2.6 moles of magnesium hydroxide? I mean, how many atoms of oxygen? Okay, we start out with what we were given, which is 2.6 moles of magnesium hydroxide. And we look to see what we were asked for. We were asked for atoms of oxygen. Now that I know what I've got, the first thing I'm going to do is look at the formulas. They are different. Different formulas mean I need the mole to mole ratio. According to the formula, there is going to be 2 moles of oxygen in 1 mole of magnesium hydroxide. The next thing I'm going to do is I'm going to look at the unit. The first unit was moles of magnesium hydroxide. I already have moles of magnesium hydroxide. I don't need another conversion factor for that one. The next thing I'm going to look at is I have atoms of oxygen. Anytime I see atoms, that means I'm going to be using Avogadro's number. So 1 mole of oxygen is going to equal 6.022 times 10 to the 23rd oxygen atoms. 1 mole of anything is 6.022 times 10 to the 23rd. Now that I have taken care of my formulas and my units, I am ready to do this conversion. Starting with the piece of information I was given. My very first thing needs moles of magnesium hydroxide. So I'm going to be using that mole to mole ratio. And from that mole to mole ratio, the 1 mole of magnesium hydroxide is going to go into the denominator with the 2 moles of oxygen in the numerator. We place the magnesium hydroxide in the denominator so that the unit, oh dear, and the substance would cancel out, leaving moles of oxygen. Now we're going to use Avogadro's number. From Avogadro's number, the mole of oxygen goes in the denominator, and the 6.022 times 10 to the 23rd oxygen atoms goes in the numerator. The mole of oxygen had to go in the denominator so that the unit and the substance canceled out, leaving oxygen atoms, which is what we were asked to solve for. So keying this into the calculator, 2.6 times 2 times 6.022 times 10 to the 23rd is 3.131 times 10 to the 24. Now looking at significant digits, my first value has 2 significant digits. The mole to mole ratio is exact quantities, so those have unlimited number of significant digits. The number in scientific notation, the mantissa, has 4 significant digits, and the mole in Avogadro's number is infinite. So looking at this, 2 significant digits is the value with the fewest. So our answer will have 2 significant digits. So we would record this answer as 3.1 times 10 to the 24 oxygen atoms. Questions? Again, it seems, now, I do want to point out something. Folks, I gave you a table at the start of class and on Tuesday prior to spring break that told you what conversion factor to use for what. But if you don't like that, you can follow along with this diagram. Let's just go back to this original question that I did. How many moles of sodium oxide is 1.5 moles of sodium? I started out with, if you look right here, I started with 1.5 moles of sodium. So I started with 1.5 moles of A, and I asked for moles of sodium oxide. Those have different formulas, so you'll notice that the conversion factor is the mole-to-mole ratio. In the second problem, I started out with grams of chlorine, and I went to moles of sodium chloride. So I started out with grams of A, and I went to moles of B. So I needed two conversion factors. The first conversion factor was the molar mass of chlorine. The second conversion factor was the mole-to-mole ratio. And in this third problem, I started out with moles of magnesium hydroxide and I wanted atoms of oxygen. So I started out with moles of A and I wanted atoms of B, which is up here. So the conversion factor was the mole-to-mole ratio and then Avogadro's number. So I'm trying to show you two different ways by which you can get to the conversion factors. This flowchart will help if this is something that works for you. For me, that table that I gave you at the start of class is the easiest. And it just helps me to pick apart what I need to solve for. You can use whichever tool works best for you. Let's look at some more. Yes.
On the last question, could you show us just really quick how you?
Okay, so there's two different ways. First of all, I do 2.6 times 2. Now, you can do it as times open parentheses 6.022 times 10 caret 23 close parentheses. If you use that form. The other way you can key this in is as 2.6 times 2. Hold on. I'm used to doing it, so let me, okay. Times 6.022. The second button, the comma, which 23. And if you do this, it'll look in your calculator as 2.6 times 2 times 6.022 E23.
So because of that, how did you get 10 to
It has to do with the fact that you're multiplying the 6 point, so technically, when you key this into the calculator, you should get to the 24th. But oh. That is because when you key this into the calculator, if you key in just this portion without the 23, you get a number of 31.3144 times 10 to the 23rd. Well, when we're doing things in scientific notation, we never, all of our values are between 1 and 10. So when you move this over one more space, that's where the 24 comes from. But if you just key it into your calculator, you should get to the 24th.
Yes, ma'am. Thank you so much.
Other questions? Let's see. Let's come up with another problem now. Let's say how many oxygen atoms are in 24.3 grams of dinitrogen pentoxide? Okay, we're going with what we were given, which is the 24.3 grams of dinitrogen pentoxide, and we want to solve for oxygen atoms. Tearing this apart, N2O5 and O have different formulas, so that means I'm going to need the mole to mole ratio. According to the formula for N2O5, there are 5 moles of oxygen in 1 mole of N2O5. The second thing I see is I see grams of N2O5. Grams means I'm going to need molar mass. So I have 2 nitrogens times 14.01, and I have 5 oxygens times 16.00. That means it's 28.02. And 16 times 5 is 80. .00. So adding this together, that is 108.02. What that means is you have 108.02 grams of N2O5 is equal to 1 mole of N2O5. The last thing I see is I see the word atom. Anytime I see the word atom, it means I'm going to need Avogadro's number. So that's going to be 6.022 times 10 to the 23rd oxygen atoms is 1 mole of oxygen. Now that I've identified my 3 conversion factors, according to the units and the formulas of what I have and what I need to solve for, I'm ready to begin this problem. You always start with the piece of information given. So the 24.3 grams of N2O5. My first conversion factor has to have grams of N2O5. So I'm going to be using that molar mass. So 108.02 grams of N2O5 is 1 mole of N2O5. The gram portion had to go in the denominator so that the unit and the substance cancels out. Now I have moles of N2O5. My next conversion factor has to have moles of N2O5 in it. So then I'm going to use the mole to mole ratio. 1 mole of N2O5 has 5 moles of oxygen. The moles of N2O5 go in the denominator so that the unit and the substance will cancel out, leaving moles of oxygen. But I want atoms of oxygen, and therefore I am going to use Avogadro's number next. The mole portion of Avogadro's number is going to go in the denominator with the 6.022 times 10 to the 23rd in the numerator. The mole portion had to go in the denominator so that the unit and the substance would cancel out. And I'm ready to solve. And when you key this into the calculator, you get 6.7735 times 10 to the 23 oxygen atoms. Significant digits next. There are 3 significant digits in the first value. In the molar mass, the mass portion had 5 significant digits, while the mole portion is infinite. Mole to mole ratios are infinite. In Avogadro's number, the mantissa of the scientific notation has 4 significant digits, while the mole portion is infinite. So looking at this, the measurement with the fewest had 3 significant digits, so our answer can only have 3 significant digits. And therefore, the answer we would record is 6.7. 6.77 times 10 to the 23rd oxygen atoms. Now key in this into the calculator. You can do this one of 2 ways. The way I key this into the calculator is it's 24.3 technically times 1 divided by 108.02 times 5 divided by technically 1 times 6.022 times 10 to the 23rd divided by 1. Meaning I key it all in one fell swoop. Now, some folks don't like that. So what you can do is you can key in the 24.3 times the 5 times the 6.022 20 times 10 to the 23rd and get an answer. And then you can do the denominator, which is just 108.02. Let's do this. You would get 7.3167 times 10 to the 25, and then divide that by 108.2, and you can get your answer. So it's whichever one works better for you. Basically, in that top one, folks, what I'm doing is I realize that each of these represents multiplication, and this line represents division, and I do it column by column. So that 24.3 first, to get to the next column, I got to cross the multiplication, so that's why it's times 1. And then I got to cross the division, divided by 108.202. And then I got to cross the multiplication, so times 5, and then I got to cross the division, divided by 1. So I do it column by column, essentially. But you can do it where you do all the numerators, get an answer, and then do all the denominators, get an answer. And that is also will give you your answer. Now, again, look at this. We started with grams of magnesium into a 5. And we went to atoms of oxygen. You will notice that the first conversion factor was the molar mass. The second conversion factor was a mole to mole ratio, and the third conversion factor was Avogadro's number. On an exam, setting it up usually gives you setting it up properly usually gives you at least 75% of the points. The correct answer and the unit is usually 2 points of the problem. But the majority of the problem comes from setting it up correctly. And when I mean setting it up correctly, I mean I pay attention to do write in the units and the formulas when you are setting it up, not just the numbers. But did you write in the units and the formulas as well? Let's look at another example. How many grams of oxygen is found in 24.7 grams of potassium dichromate? Okay, so we start with what we were given, which is the 24.7 grams of potassium dichromate. And then we identify what we want to solve for, which is grams of oxygen. Looking at this, the formulas are, different. So that means I'm going to need a mole to mole ratio. According to the formula, there are 7 moles of oxygen in 1 mole of potassium dichromate. The next thing I notice is I have grams of potassium dichromate. Grams means molar mass. So I have 2 potassiums times 39.10. Trying to use the same thing I give you. I'm pretty certain it's 39.10. I have 2 chromiums times 52.00. And I have 7 oxygens times 16.00. So 78.20, 104.00, 112.0. So keying this out, potassium dichromate has a molar mass of 294.2, and that's going to be 294.2 grams of potassium dichromate is equal to 1 mole of potassium dichromate. The next thing I see, again, I'm picking this apart, is I have grams of oxygen. Again, grams means molar mass. So in this case, I will need the fact that there are 16.00 grams of oxygen in 1 mole of oxygen. Now that I've picked it apart and figured out the conversion factor and determined what the conversion factors are going to be, I am ready to key this into the calculator. I start with the 24.7 grams of potassium dichromate. My first conversion factor will need grams of potassium dichromate. Therefore, I'm going to use the molar mass. From the molar mass, the 294.2 grams of potassium dichromate will go in the denominator, with the 1 mole of potassium dichromate in the numerator. The grams had to go in the denominator so that the unit and the substance would cancel, leaving moles of potassium dichromate. My next conversion factor needs the moles of potassium dichromate, and therefore I'm going to use the mole to mole ratio. For every 1 mole of potassium dichromate, there are 7 moles of oxygen. The mole portion of the moles of potassium dichromate went into the denominator so that the unit and the substance would cancel out, leaving moles of oxygen. But I wanted grams of oxygen, and therefore I need my third conversion factor, which is the molar mass of oxygen. In the molar mass of oxygen, the mole of oxygen will go in the denominator with the grams of oxygen into the numerator. The moles of oxygen went in the denominator so that the unit and the substance would cancel out, leaving grams of oxygen. Now that I have everything, I am ready to solve. And you get an answer of 9.40313 grams of oxygen. The next thing you need to do is figure out significant digits. Your starting value has 3 significant figures. The molar mass of potassium dichromate has 4 significant digits for the mass, and it is infinite for the moles. The mole to mole ratio are infinite because they're exact numbers. And then the mass for the molar mass for oxygen, the mass portion had 4 significant digits, while the mole portion is infinite. And therefore, looking at this, the measurement with the fewest had 3 significant digits. So you would record your answer as 9.40 grams of oxygen. Questions? Any questions where I'm getting these numbers from? Yes.
So I understand where you got the COS 52, the OS 16. How did you get 29?
Should have been 39.
Oh,
Other questions? And I'm remembering these off the top of my head, so I'm hoping I'm not memorizing them wrong or having them wrong. Let me give you one to work. I've given you several examples, so let's see how it goes. Why are you doing this to me, people? Get rid of this. And put the answer on the board. So you can check your work. I'll also illustrate or do it here in a few, but I thought I would let you see how you did. Okay, so looking at this, I wanted to go from 2.96 times 10 to the 24 chromium atoms to grams of chromium. First of all, I looked at it and the formula of chromium is the same. So I'm not going to need a mole to mole ratio. Then I looked at the individual units. The first thing I saw was the word atoms. Anytime I see atoms, ions, or molecules, I automatically go to Avogadro's number. So that's going to be 6.022 times 10 to the 23rd chromium atoms is 1 mole of chromium. The next thing I noticed is I had grams of chromium. Anytime I see grams, that automatically means I'm going to need the molar mass. So looking at the periodic table, 1 mole of chromium is 52.00 grams of chromium. Now that I've got my conversion factors, I'm ready to begin this problem. I'm going to start with the 2.96 times 10 to the 24th. Chromium atoms. My first conversion factor is going to need chromium atoms, and therefore I'm going to be using Avogadro's number. Avogadro's number goes into the denominator. With the 1 mole of chromium going in the numerator. Avogadro's number had to go in the denominator so that the unit and the substance would cancel out, leaving moles of chromium. The next conversion factor also needs moles of chromium, so I'm going to go to the molar mass. The molar mass, or of the molar mass, the 1 mole of chromium goes in the denominator with the 52.00 grams of chromium in the numerator. The moles of chromium went into the denominator so that the unit and the substance would cancel, and you were left with grams of chromium. When you key this into the calculator, you get an answer of 255.596 grams of chromium. Now, significant digits, your first number being in scientific notation, we looked at the mantissa, it had 3 significant digits. The Avogadro's number, the scientific notation has 4 significant digits because there are 4 digits in the mantissa, while the mole portion of Avogadro's number is an exact quantity and therefore has an unlimited number of significant digits. The molar mass, the mass portion had 4 significant digits, while the mole portion, again, is an exact quantity, and therefore it has an unlimited number of significant digits. Looking at these measurements, the one with the fewest had 3 significant digits, so our answer can only have 3 significant digits, and that is why I rounded the answer to 256 grams of chromium. Now, keying this into the calculator, it all depends upon how you do it, but if you use times 10 carat, make sure you have your parentheses, because if you forget a parenthetical piece, it is going to give you the wrong answer. So keying this into the calculator, if you use times 10 carat, it would be 2.96 times 10 carat 24 divided by 6.02. 2 times 10 carat 23 times 52. Now, if you use my method, you don't have to worry about parentheses, and it would be 2.96 second, comma, 24, divide 6.022 second, comma, 23 times 52. And the way it actually looks in the calculator is 2.96 24 divided by 6.022 times, or 23 times 52. So it depends upon how you key it into your calculator. Questions? Okay, on Thursday, we're going to balance chemical reactions. So we're actually going to start dealing with not just the elements, not just compounds, but we're going to get into chemical reactions, which is the chemistry part. I mean, it's all chemistry, but we're going to actually start doing the science that is the chemistry that we typically think of as chemistry. And I will see you on Thursday. Again, if you are questioning whether to drop the course or not, the deadline, I'm pretty certain, is Monday. And I will hopefully have your test graded by Thursday, but if not, you can come see me individually and I will calculate your grade.